let y of x be the function that solves 1 plus e to the x all times dy dx plus e to the x times y equals to the sine of x, with the initial condition that when y is evaluated at 0, you end up with a half. And you're asked to find the function y of x. Before you start, you must have it in standard form. This is a linear ordinary differential equation, and the standard form for it is dy dx plus p of x times y equal to q of x. What we have is 1 plus e to the x times dy dx plus e to the x times y is equal to the sine of x. This 1 plus e to the x can't be in front of the dy dx, so we divide by it. And we identify exactly what is multiplied by y. Because the next step in the process is for us to find the integrating factor, and it starts with you integrating p of x. How do you integrate e to the x over 1 plus e to the x? Well, you need a u sub. Let u be the entire denominator, because its derivative is basically the numerator, e to the x dx. So you'll be integrating 1 over u du, which is the natural log of u. So the antiderivative of e to the x over 1 plus e to the x is the natural log of 1 plus e to the x. Why do we need this? The integrating factor, mu, is the e to the integral of this, p of x dx. And so we then replace the integral of p of x dx with the natural log, and these guys can cancel. So it turns out that your integrating factor is 1 plus e to the x. Okay, great. Well, now what do we do with this? Here's our standard form equation. Here is our condition. Here is our integrating factor. Multiply that equation by the integrating factor. So 1 plus e to the x gets multiplied by all three terms, and we cancel on the right hand side. Not necessary that we simplify on the left hand side, but let's do it anyway since we can. At least cancel out those, and we're left with the following equation: the quantity of 1 plus e to the x times dy dx plus e to the x times y equals the sine of x. Actually, that's where we started at, but it's hard to know that we could have gone from there to where we're about to go. And the reason why you introduce the integrating factor is so that you can rename the left-hand side to be the derivative of the product of the integrating factor times y. Just a renaming, just rewriting it. And so integrating factor is mu, 1 plus e to the x, and we multiply that by y. And we have the derivative of that. This symbol means take the derivative of what's to come after that. Right hand side, after canceling, we just have sine of x. So in the next step, we'll integrate both sides. Let's do that on the next slide. Integrate the left and integrate the right. And so when we integrate the left, we employ the fundamental theorem of calculus, and these operations cancel each other out. That's what's so special about the integrating factor. After multiplying through by it, it turns your left-hand side into a product rule, and then after integrating that product, you just get the integrand. On the right-hand side, we have to remember that once we integrate the right-hand side, we need to put plus c on it. What function has sine of x as its derivative? Not just cosine x. Okay, we're going to have negative cosine x. All right, great. Well, then what do we do next? Immediately, we have to get this c out of here, I believe. It's useful, I think, to get it out of there. So we need to plug in this condition. When x is 0, y is a half. So we plug that in. E to the 0 is 1. 1 plus 1 is 2. 2 times a half. This entire quantity is a 1 on the left-hand side. Cosine of 0 is 1, but times that negative, we end up with a negative 1 plus c on the right-hand side. And adding the 1 over, we get that c is 2. Immediately go back to your current form of your solution and plug in the 2. What you end up with then will be 1 plus e to the x all times y equal to negative cosine x plus 2. Okay, great. And they just want us to find out what y of x is. So we'll answer that question. We'll solve the problem by dividing through by 1 plus e to the x. And pretty much that's your answer. Maybe reverse these two and call it 2 minus cosine x. That's the function that solves that original differential equation with the condition that was given.